Thank you very much for the opportunity to talk about life cycle analysis, especially with the grid model we developed at our national lab. So I'll go through and I will keep your set your copy and you can distribute among the faculty members. So the trend of life cycle analysis. Some of you may know, and some of you may not know life cycle analysis. So life cycle analysis is a holistic way to evaluate technology's environmental footprint. So historically, let's say if you drive a car, we care say how much emissions we produce from our car's tailpipes. But now with life cycle analysis, we push all the way to how the gasoline is produced, how the car is produced. So that's kind of from a single point of view to life cycle point of view. So in this way, the environmental effect shift from one stage to the other stage of the whole system is not missed. And the life cycle analysis thinking already help us as individuals and companies as corporations to think about our behaviors and about our decision making. Some of us go to grocery stores and get a product, and some product has the so-called sustainability certification. Sustainability certification for products generally take life cycle point of view, so how products produced, and how the feedstock produced, how the product get from the production site all the way to supermarket shelf. So that's the holistic point of view. In the transportation area, that's where grid LCA is studied with. There are some significant programs and regulations now based on life cycle analysis. For example, the US in California, the so-called low-carbon fuel status, and in several other states such as Oregon, the state of Washington, and now under discussion in Vermont, New Mexico, and the state of Illinois. The EPA's renewable fuel standard. The Inflation Reduction Act has significant incentives for clean fuels, and I'm going to touch on this, and the incentives based on LCA results. Internationally, I know you have some sustainable aviation questions here. So the International Civil Aviation Organization, this is one of the 5 UN organizations, have developed a program called COSIA. So COSIA is based on LCA. In fact, I was at a conference call, that's why I'm a little bit late to the COSIA working group. 7 a.m. You're still going on. You will talk about what the update, what's the expansion of the COSIA program. The International Marine Organization now contemplates something similar to LCA for marine decarbonization, the EU program, the Canadian program, and the Brazilian program. So internationally now, LCA is used for regulation with compliance. So now you expand the LCA a little bit. So life cycle analysis is primarily from the technology and the product point of view. So if we introduce battery electric vehicles, we want to evaluate greenhouse gas footprint of battery EVs versus gasoline vehicles. That's technology LCA. On the other hand, our enterprise area, companies now have sustainability report. In sustainability report, companies are required to report the so-called Scope 1, 2, and 3 emissions. Scope 1 emissions are the emissions they generate from their facility themselves. Scope 2 emissions is the emissions embedded in the materials, the energy, the steam, electricity they purchased. Scope 3 emissions are the employee travel, the facility, and all the other indirect activities. So as you can see, the 3 scope emissions is LCA, but from company's point of view. And right now, the 3 scope emission reporting is voluntary. So companies report in the sustainability report, but SEC now has a requirement for publicly traded companies to report as 3 scope emissions, at least the scope 1 and 2. California already required public companies has business in California report 3 scope emissions. So this is the way to summarize these 3 scope emissions: scope 1, scope 2, and scope 3. So in a way, you can see its life cycle analysis from the company's operation point of view versus the product life cycle or supply chain point of view. So great. We have history of 40 years to develop the great LCA model, started in 1994, and with the long history, we now have annual release of GRID. So GRID is, and the GRID website, as you see here, and we make this available for your public to download and use. GRID has 2 major components, the so-called GRID 1. This is where I alluded earlier. Let's say if we have electrical cars, how the electricity is produced. If we have gasoline cars, how the gasoline is produced, all the way from the oil field. On the other hand, we have GRID 2. GRID 2 can be look at how the cars are produced. The ore for steel, aluminum, the petrochemicals for rubber, plastic, and so on. They all are here. And the batteries for EVs and batteries for EVs are here too. So now, as you see, the 2 together give you a holistic point of view. Now, when we drive for our car, we know how much emissions are associated with making the car, and how much emissions are associated with the electricity, the gasoline, the diesel we use to drive the car. So that's kind of your high level of GRID LCA covered. What type of result we produce from GRID? So the 4 groups, the energy used by different types. So we care about how much fossil energy used. So your GRID generate that. So this is kind of your energy availability and energy secure. Air protect. Historically, when I started GRID in 1993 and 1994, this was the key area because back there, urban air pollution is significant issues for U.S. government, state government to address. So we put a lot of effort here. Of course, in the last 15 years, we put more effort on greenhouse gas emissions of technologies. As we all know now, greenhouse gas emissions are significant for climate change. And economy-wide decarbonization now is a significant demand for greenhouse gas emissions of certain technologies if we deploy for decarbonization. Water consumption is a significant issue, especially in certain regions like western U.S., southwest U.S. So these are the 4 groups from GRID LCA. As I mentioned, GRID is available from the GRID website, so you can go there. And this is the GRID open page and see. So the models are here, as you see, for different versions and different modules from GRID. And we have a lot of publications. we have done training workshops. So if you click here, you're going to see our training workshop materials. So if you're interested to download great use, these materials will help you to start do the high level LCA. And gradually, if you want to do deep LCA, great will give you that. So now your turn to say what covered in great. Great covers energy systems extensively. This slide summarizes what energy systems covered in great. So as you see here, we have petroleum-based energy systems, gas, diesel, jet fuel, etc. Natural gas and other sources to hydrogen. We know now hydrogen is an important area with the federal government's $9.5 billion investment in hydrogen economy, with $8 billion in the so-called hydrogen production hubs, $1.5 billion in electrolyzer to produce clean hydrogen. The so-called e-fuels, this is where we combine what is the CO2 and renewable electricity to renewable hydrogen, produce a new carbon neutral liquid fuel. Of course, different natural gas systems. Natural gas, we have conventional, we have shale gas, and we have renewable natural gas, and we have other waste streams such as coal mine, electricity generation, and we know electricity is generated from different energy feedstocks and with different generation technologies. So here we cover all the electricity generation technologies with different energy feedstocks. This whole block. Biofuels, and I see you have some questions about that, and biofuels, they're all in this block. So different feedstocks. In the US, we produce large amount of ethanol from corn, larger amount of biodiesel and renewable from soybean and waste oil resources. So overall, we have more than 100 energy systems covered in great LCA. And besides energy systems, we cover the materials extensive. So we have different chemicals, production, and life cycle, and different materials such as steel, aluminum, even cement. Because these are the materials we need to build our energy infrastructure, to build cars, trucks, aircraft, so and plastic. Extensive coverage plastic in rate and other byproducts for your sustainability improvement. So these are the material groups covered in grid beside energy systems. As I mentioned, grid started on transportation LCA model. For transportation, we cover the road transportation, cars, trucks, SUVs, pickups, air transportation, aviation, we mentioned the sustainable aviation fuels, and of course, efficient aircraft, rail, and marine. These two now are the so-called, actually, these three are the so-called hard to electrify transportation sector. So electrification now has significant role to play here, but for these other three sub-transportation sectors, liquid fuels, lower carbon liquid fuels, still have significant role for decarbonization. So here is on slide summarize grid user base. So we have about 60,000 registered users globally. of course, North America is more than half of our global users. And the academia and educational institutions, this is where you're from, are about half of our users. Why will this whole group is half? Because now in universities, in undergraduate curriculum and undergraduate curriculum, LCA now has introduced into classes to train the students with LCA understanding and hands-on LCA, so they can examine the technology sustainability impact themselves when they go up to work in companies. Because there, as you see, many companies, they are indeed the intensive grid users. And these companies has internal LCA teams, and many other companies use grid to do LCA. So training students with LCA understanding and skill set will empower themselves in the workplace, in the current situation, because the technologies are introduced for decarbonization. They need to know how to evaluate the carbon footprint of the specific technologies that work on it. And I mentioned the regulations use of grid. So here is the summary of grid use in different regulations and programs. I mentioned the California low carbon fuel standard use grid, and the Oregon Clean Fuel Program and the state of Washington program. They all use grid to look at the specific fuels carbon intensity for their regulation compliance. EPA use grid for renewable fuel standards. And you already mentioned the ICAO's COSIA program relied on grid, but the Canadian Clean Fuel Program relied on grid too. But most significantly in 2022, the Inflation Reduction Act has significant incentives for clean energy. The clean energy's incentive level is based on the carbon intensity of specific product. So let me show you. So this is the IRA Inflation Reduction Act, the so-called 40B provision for SAF incentive. So this is sustainable aviation fuel incentive. For each gallon of fuel produced, the incentive could be from $1.25 all the way to $1.75, but depending on carbon intensity of LCA. Congress specifically said carbon intensity will based on the ICAO COSIA program, which I'm part of that program, or the similar methodology to EPA. We, in the last half year from December to April 30th, developed a grid version to make that grid version to qualify as the similar methodology to EPA's RFS. So that version now is released on April 30th by the Internal Revenue Service together with DOE. So people will use that to decide the carbon intensity. So the trader will use this to decide the incentive for that. Same thing for clean hydrogen. Clean hydrogen is under 45V provision in RA. So as you can see, the clean hydrogen incentive can go as low as about 60 cents per kilogram of hydrogen, or all the way to $3 per kilogram of hydrogen. But again, the incentive is based on carbon intensity of hydrogen. Now, the carbon intensity is decided by grid. So Congress puts that in law. So grid is going to use to see where you are on carbon intensity. The trader will decide the incentive level based on carbon intensity. So that's clean hydrogen. At 45Z, provision as clean fuels. So the other liquid fuels, such as renewable diesel and other liquid fuels. And again, as you see, you select if this is done per gallon based on carbon intensity. And the carbon intensity, again, comes set based on Argus grid. So we are work on this grid portion. This is already done as December. This was done in April 30th. Now we'll work on this. So there will be 3 grid versions for RA incentives companies will use at the Treasury and the DOE will certify. So now, what is LCA? So you may wonder, you show me how important, but what exactly LCA is all about? So this chart gives you a sense of what LCA includes. This is the gasoline diesel as an example. So as I mentioned earlier, we start with crude and natural gas in oil and gas field. And we have exploration, recovery process in the field. We have transportation of crude to refinery. Because crude is a global commodity. So you produce in oil field in Mid East, Canada, Central America, and you transport to refineries globally. For U.S., our refineries are in Gulf Coast area. Chicago has several refineries, and the West Coast has some. So transportation, the refining, the fuel transportation, we get our gasoline from gas stations, but gas stations use trucks to take the gas from bulk terminals to a station. So that's part of LCA. They finally, when we drive the car, burning gasoline or diesel. So that's kind of what LCA means. You cover the whole supply chain of our product all the way to the end. So this is the gasoline. Of course, there are some key issues affect LCA result. So here, with this table, summarize a specific issue to affect natural gas-based energy systems. We use natural gas to generate electricity. Our homes use natural gas for space heating and for cooking. Natural gas from gas field all the way to our home, or to electrical power plant. We have pipeline distribution system, we have compression, we have process. This whole process has natural gas leaked. Likely our homes does not have, because if we have gas leakage will smell. That's a safety precaution. You smell that you have a problem. But the pipeline, the process plant has leaks. The leakage rate affects your natural gas-based systems significantly. So here are the different studies summarize how much the natural gas system leaked. Natural gas during this whole production, storage, and distribution. You see the studies cover all over the method. Some said it could be as high as 7%. Some says maybe less than 1%. If I use 1% versus 7%, that will change the natural gas-based energy systems LCA result big time. Why? Because methane is about 40 times as potent as CO2. So you multiply each gram of methane by 30, suddenly it's become a significant greenhouse gas. Data is key. So these are the summaries of our data sources. Because you now say, okay, so you have the whole supply chain for a specific product, but each stage you need data in order to quantify the greenhouse gas emissions, energy use. So how do you get the data for each of the activities on non-supply chain? So here, as you see, we rely on government statistics there are several government agencies as annual statistic databases release. The field operation data, so the power plant operation, the oil field operation. The operations data are important data sources. And therefore, new technologies, we know there is no operation. So we do a lot of simulations. So simulations, this is what we're good at the national labs, do very detailed simulations, generate energy and mass balance for technologies we evaluate. The collaboration with universities, national labs, and trade associations, these are the significant data sources for GRID. In fact, GRID's value is databases as well as serve as an LCA tool. Many of the users come to GRID for the data they need for their research. So databases in GRID now is a significant asset for GRID and for the technology community. So I mentioned data is the key, and when we evaluate data, of course, data representation is the key. So if we look at your data, do we look at the data to represent the operations now or represent the operations in the past? So as you see, the SR pad yield continue to improve. So if we use data here versus data there, it will give you a different LCA result. Except similarly, the core yield in fibs, this is a national average yield change over time from 1990s all the way to 2019. And ethanol platinum, so they all give you the historical trend. So the so-called temporal representation is key in LCA and in building the LCA databases. This is the biofuel system boundary. So now if we're going to evaluate sustainable aviation fuels, or simply we call SAF, what is the LCA system boundary for SAF? So we start with the very first stage. As you see, the system boundary here is different from the oil and gas system boundary. We start with fertilizer production because your farming requires larger amount of fertilizer. So that's within the LCA system. And the farming stage, fertilizer application, diesel use for tractors, and tool emissions from soil, they're all part of the LCA. That fuel conversion they use, and you may or may not heard the so-called indirect land use change for biofuels. This is a significant issue. So we have indirect land use changes included as part of the system boundary for biofuels analysis. So this is the biofuel system boundary in GL. So now with the temporal representation, you can generate a carbon footprint over time. So this is the U.S. average core ethanol result from 2005 all the way to 2019. So the downtrend in carbon intensity is a reflection of what you see earlier, the farming yield change, the energy use change, and the ethanol yield change. They all kind of as input into GRID. The GRID generated core ethanol carbon intensity result as you see here. Furthermore, so this is interesting for your policy makers. Okay, I'm going to incentivize biofuels. I want to see the carbon intensity of specific fuels, but more so for your for those of us in research in education institutions and in research community in general, we're interested in where the greenhouse gas emissions are from. So grid give you the sources of greenhouse gas emissions. So as you see, farming is significant, ethanol plant is significant, land use change is significant. These are the significant contributors to the overall result. So this type of insight will help us to see if we want to reduce the carbon intensity, where we should put effort on, because we know where are the significant sources. So this insight help R&D, help technology deployment. In fact, right now there are a lot of activities going on carbon capture and storage, CCSU ethanol plant. But if we have CCSU ethanol plant, that's your fermentation CO2 from start fermentation. That will pretty much make this almost non-zero. So technologies and come in play a significant role to drop down the carbon intensity further. So working in national labs to develop grid will not only just give people a conclusion, we'll work up your ideas to give people the insights where the effort had been made to drop down your carbon footprint or environment footprint in general. So here is a slide how we use grid to analyze. If we say we want to drop down carbon footprint for your business corn to ethanol, that ethanol to jet fuel SAF. So step by step, we know the sources as you think here breakdown, and we now say, okay, what are the opportunities? If we reduce it, if we introduce clean hydrogen, that will give us 3.7 grams per megajoule reduction, or if we induce renewable power, or if we have biogas to replace natural gas, or furthermore, if we install CCS, carbon capture and storage, or if we have climate smart agriculture practice. What are each step's impact to drop down carbon intensity for a specific technology? That's what grid is much higher value for researchers to use and for engineers to use. And that's why universities now train the undergraduate and graduate this skill set, so they can look at technologies and they can look at the sustainability impact. So SAF, sustainable aviation fuel. So COSIA and ICAO had this ambitious goal to make the aviation sector carbon neutral eventually. But what are the ways to achieve that? Sustainable aviation fuels will play an important role because we know aviation sector has much less options than the road transportation. So to identify the lower carbon SAFs, key. So that's why the COSIA program has been in place since 2017. Now, the airlines have international operations now under the COSIA requirement to reduce their carbon footprint. So how are they going to reduce carbon footprint? So they can use SAF, as we summarize here with grid, or they can increase their aircraft efficiency or operations efficiency. So efficiencies and SAF are two ways. So SAF, depending on what feedstock you use to produce SAF, and how you produce SAF with a given feedstock. So carbon intensity, as you see here, vary significantly among all the SAFs. So that was documented by us and 3 other organizations, the EU Joint Research Institute, MIT, and there are a couple of universities in Europe and Canada. So 5 organizations work together to develop this this chart is already in the LCA document. And we'll continue to update what you see here. We're expanding more safe production options under the IKEA Fuels Task Working Group. So electricity. So electricity, of course, we need electricity for our your daily life. The battery EVs need electricity. The electrification of other sectors have significant electricity demand. This chart summarizes the electricity LCA in green. So we have different energy feedstocks here. And we have process transportation of the feedstocks to power plant. There we have electricity distribution to our homes. And of course, we also include the construction of power plant, solar PVs, wind turbines, and hydro dams. They're all part of the life cycle analysis in green. So this is the electricity LCA system boundary. So with that, now we know regionally each U.S. region has different power plant generation mix. We in Illinois has a significant amount of our power from nuclear power plant. And the Western United has a significant amount of hydro power. The upper Midwest here still have a significant amount of coal-fired power. So the generation mix have result in very different carbon intensity for electricity, as you see here. This is carbon intensity in grams of CO2 equivalent per kilowatt hour of electricity available at our home. So at the state level, we can generate electricity carbon intensity. And over time, we can generate carbon intensity. So this is the base of the prediction of the U.S. generation mix over time. And we know coal-fired power plants continue to be retired. Natural gas power plants now step in, but gradually to be reduced. When solar continue to increase, as you see here. So that will drop down our carbon intensity for the U.S. electricity over time from 2022 to 2050. So grid can generate the temporal variation as well as spatial variation for electricity carbon intensity. So with this, now if you have battery EVs, you can say, okay, if I'm in Chicago, my electricity carbon intensity roughly is about 400. If I'm in California, mine is maybe about 350 grams per kilowatt hour. So depending on where you drop your EVs and get your electricity, your greenhouse gas performance will be different. Hydrogen. So let's talk about the embodied carbon in the context of hydrogen and in the context of electricity. We know solar electricity, when we generate from solar PV, is carbon-free. But production of solar panel is not carbon-free. So that's what we call embodied emissions. So this is the solar PV embodied emissions, roughly about 40 grams per kilowatt hour, versus our average. Our national average is about 400. So it's 1/10 of our average electricity. So it is small. But on the other hand, that's your solar PV. This is the electrolysis, because to produce hydrogen, we need an electrolyzer together with electricity. So electrolyzers, your electricity the electrolyzers embody the carbon emissions in grams per kilogram of hydrogen. So depending on what type of electrolyzer your carbon capacity could be 30 grams to 75 grams per kilogram of hydrogen. This is per kilogram of per kilowatt hour of electricity. This is the per kilogram of hydrogen. So the two different units, right? We know for each kilogram of hydrogen, we need 55 kilowatt hour. So if we multiply everything here with 55, we're going to agree to that into here per kilogram of hydrogen. So 40 multiplied by 55, that gives us about 2.1 kilograms of CO2 per kilogram of hydrogen. So where is 2.1 kilograms? 2.1 kilograms, the way up here, because this is only 80 grams, not kilograms. So when we breathe this is more significant than the electrolyzer embodied greenhouse gas emissions. So that all can be a part of the breathe LCA. So this is the hydrogen system boundary. So we have different ways to produce the so-called clean hydrogen from electricity, or the conventional way from natural gas. And then, of course, hydrogen needs to be stored and transported. That's part of our application value, hydrogen different applications. So this is our ecosystem of hydrogen system, LCA. And then, this is the conventional way to produce hydrogen from natural gas, steam methane reforming process to hydrogen and transportation. And this is the electrolysis hydrogen with electricity. Of course, electricity is from different feedstock. So that's part of electrolysis hydrogen production. And now when we have different hydrogen production pathways together, this is where we get our hydrogen. Now globally 90% of hydrogen is produced from this pathway. So roughly it's about 10 kilograms of CO2 per kilogram of hydrogen. If we move into this clean hydrogen, it's almost here. This does not include the embodied greenhouse gas emissions, as I talked about previous time. So this gives people a high level say, okay, I know the 45 billion Inflation Reduction Act has up to $3 per kilogram of hydrogen incentive, and in order to get 3, my DHG cannot go above 0.45, so I'll look at 0.45, and which pathways qualify for that. Then I can pursue the project based on the pathways in order to get $3 per kilogram of hydrogen incentive. $3 is very significant. The current hydrogen production with this pathway roughly is about $1.50 to $2. But these production costs are much higher. That's why Congress provide up to $3 in order to bring down the cost of these pathways close to this pathway. So that's a quick summary of GREAT and the important technologies covered in GREAT and some results. So in summary, LCA is a major step to holistically evaluate sustainability of technology policies. The GREAT model developed has benefit from continual improvement in the methodology, the data in LCA community. So I'm in LCA research, and LCA is research with our community. And of course, DOE support as benefit our 30 years of great event. And of course, the methodology as a result need further improvement. The methodology continue to expand, and you got a sense about the system boundary. So the biofuel system boundary is different from clean hydrogen system boundary. This is still an evolving topic, so there is no fix. Everybody say, okay, this is it. This is the system boundary. This is a very dynamic area. Of course, your data are the key. So, with that, the website, of course, has models, publications, and user instruction materials. So, thank you.
Questions here now?
Yeah.
Well, I have 4 pages of questions.
Please.
That was brilliant. Thank you so much.
So I'll make this available to you.
Great. So I don't even know where to start with my question, but the first thing is when students in sustainability are looking for jobs, one of the skills is understanding LCA, right?
Yeah.
And there's very little training on that, if any, in colleges and also universities. I don't know, maybe I'm speaking out of line and all of you teach that in your, but it's almost like the number one skill that companies are looking for. And so my question is, do you have an in-depth training module to share with all of us that we can teach this to our students?
Yeah, we do. The workshops as are taught up and read the website. The most recent workshop we ran was November 2022. So we have we had a 1.5 day deep dive training. We have presentation materials posted there. So that's a good start. And we also have YouTube videos on YouTube, a great channel at YouTube. So you can go to the GRID channel from the GRID website, or you can do a search of GRID in the YouTube website. Get into the YouTube videos for your quickly learn GRID and start GRID. These are the materials will help people to jumpstart.
You said there's a deep dive training?
Yeah, the workshop, as I showed, the GRID website.
Okay, and do you have one coming up for like educators, to teach educators how to teach this?
Yeah, let me get here. I'll talk about it. So if you click the workshop here and the GRID website, all the presentation materials are there. So I will have a workshop coming not anytime soon. So now we think differently. We start our effort we call trade trainers. So we're going to recruit up to 20 trainers nationwide. And we're going to train 20 trainers. They're going to conduct a regional training workshop as we did historically ourselves, because now the group is just so busy to work on the new LCA issues and develop different versions for RRA. We just do not have time to do a training workshop. So that's the new plan.
So you say like this GRID is based on so many databases, historical database, process database. So, and if I just compare with other tools like OpenLCA, they use like C4 database or LCA database.
Yeah.
Does GRID have their own database for the LCA modeling?
Yeah, so GRID has its own database. You can invite use GRID to supplement their data. And Gabby, you can invite the overcome because GRID is in public domain, free to use. You can invite Gabby, you have to pay a significant annual fee So it's a one-way street. And we are now make grid interoperable with open LCA. So that will be done by early next year. So grid database will organized under open LCA, so it's easier for other softwares to use grid databases, and we're going to be able to benefit from other databases too.
So I know some of the data will be large, but like, are the process data, can we able to edit that? Like, can we see what is input and output flows in particular pathways?
Yeah, that's clearly laid out in grid.
Okay.
The so-called background and foreground data. So we're a little bit deeper dive between two of us. The rest of the group may be confused on what we're talking. So I imagine you have some experience in everything. Yeah.
Yeah, I'm writing grants, so that's how I learned.
Yeah. You are quite already done to the next level.
I have a question that kind of dovetails off of that. How are the parameters that are set in there derived? Is it averages of consolidated data? And then are you able to adjust those parameters if you agree or disagree with what the valuation?
Grid default is US average. So if you do not change anything, the results you generate represent US average. Okay. If you have your foreground data, let's say you have a specific project, and you have your plant operation data, your override the grid default data. Now, you generate LCA results specific to your project with your foreground data. Your foreground data reflect your plant operations. There's still not a background data. Let's say if you build on natural gas power plant, you know your efficiency, you know how much natural gas you use for your electricity. That's your foreground. But then your natural gas recovery methane leakage, you have no control. So that's why we built the national average. We call those as background data. So you can just leave background data as it is for consistency. If you build another natural gas plant, you have your foreground data. That's both of you use the same background data. So that's where the consistent comes from.
I have a question regarding the boundaries when you show the example of the SAF, for example, and the one I know we had to set the boundaries, but what if we start from waste, for example, all the production of this waste in the generation of waste, we don't need to include it in the...
If we start from waste, we make decisions where is the system boundary for the waste. I'll give you a specific example. Let's say if we use municipal solid waste, MSW, we say our starting point is your MORPH. Your MORPH is where the garbage gets in, the sort, get plastic out, different materials out. So we started from there to sort the MSW for SAF production. So the sorting, the transportation, clean up, of course, the SAF production. We do not go all the way and say, okay, how about our activities to produce garbage?
Yeah.
That's part of the background system is already happening. So that's how we define. The complication is not say where is our starting point. Everybody agrees the sorting facility should be the starting point for MSW. The complication is the so-called counterfactual scenario. If I do not use MSW for SAF, what is the fate for MSW? We know it's garbage. We know it's add up in landfill. That's the current practice. But now I take that away. That means MSW does not go to landfill anymore. This is the so-called counterfactual scenario. The counterfactual scenario has emissions. The lead fuel generates methane, as we all know. So now when we eliminate counterfactual scenario, the emissions we eliminate is an emission credit for MSW-based set. This generates a whole sort of uncertainties. So what is my counterfactual? How much emissions under the counterfactual? It just generates whole sort of uncertainties, not of technical complications, that we address all those very thoroughly in grid. The counterfactual emission credit can be huge. Lead fuel gas give you up to 400 grams per megajoule counterfactual emission credit, versus gasoline carbon intensity is only about 93 grams. So you have 400 grams as a credit against your baseline. So that's why the whole renewable natural gas in the last 10 years keep going up big time, because the incentive is so huge from the counterfactual scenario, right? So that's the complication.
So going back to the IRA, are you seeing that funding is coming out of the IRA by producing these LCAs? Like if a municipality or a company, let's say a municipality is looking for grant money and they produce these LCAs, but they're looking for the IRA grant money.
Yeah. Well, it's the incentive.
Yeah.
It's not, So let's say if a municipal, your government wants to use their waste water treatment plant sludge to produce safe or clean fuels. If they go through grid LCA, they show to RS, my carbon intensity is 20 grams. They're based on the 20 grand. They RS, okay, this is the incentive. Let's say $1 per gallon of the SAF you produce. Here is your incentive. This is tax incentive. So municipal government does not have tax liability, right? So they cannot take that advantage. So Congress realized without tax liability, even you have tax incentive, you cannot realize. So they made the tax incentive tradable. So I do not have tax liability, but you do. I can sell my tax incentive to you. So now, even without tax liability, you will still realize your tax incentives by trading to somebody else.
So if you have time. So I think it's an interesting model. I'm curious as to how you assessed the accuracy of the model itself. So,
the accuracy of the model is based on the reliability of the data. So the common frames, garbage in, garbage out, if you do not have reliable data, then your result is not reliable. So your whole grid get itself into this level now. The priority regulations use Congress now goes even to law. Because over 30 years, data has been our main effort.
right.
But do we have the data set 100% reliable? No, we're not. We know where we have very reliable data, where we still have unreliable data. So with that, that's the reality. So with that reality, transparency is the thing. Tell people what data, what source, which is reliable, which is not reliable. Transparency help people to take effort to improve data. So that's why when you download the grid, you see everything. everything is just your spreadsheet, you see. That's transparency.
I have one more question. Sorry. It's probably quick. So, do you have any case studies showing GREET's impact on sustainability policy?
Such as,
Has it changed any, using your model, has it changed it, has it changed or has it the impact on sustainability policy on local and federal?
yeah,
Policy.
so yeah, the California LCFS is the most significant recognition globally. That changed the whole transportation fuel supply in California in a much more significant way. I did not envision it when they put that in place in 2009. Let me give you an example. As of last year, California's diesel market, their diesel market is small. So California's diesel market has 60% of renewable diesel blended into their diesel. You do not see that anywhere else. Why? Because renewable diesel under the California version of GREET has so much lower carbon intensity, so it generates so much incentive people produce and ship renewable diesel to California. A sad story that generates scandal too. So now people see significant down values at the table, so scandals happened too. So I'll give you an example. I think you point to what scandal are you talking about. Used cooking oil to produce renewable diesel has very low CR score. With lower CR score, LCFS has significant monetary value. So if I have some virgin oil, if I take a truck, go on your trip, they claim that's used cooking oil. That's worth more than the virgin oil to produce renewable diesel.
Thank you.
Wouldn't the economists call that an example of perverse reaction?
Exactly right.
It's only because California has such a progressive standard that vegetable oil is being used in this fashion.
Yeah, there was two, they called, in EU they called Wang. So if I have your ocean tanker of vegetable oil, if I make a round trip somewhere else, then I claim that's used cooking oil. Suddenly I generate so much monetary value.